Yeah, I've been making these slides over the past few days in my hotel room. Not as much time to prepare as I would normally take for a talk, but I hope I managed to get my ideas across anyway. So my talk is called Layer-Based Infinite Procedural Generation, Chunks and Context. I'll say a few words about what the talk is going to about, then a few words about myself. So generating infinite worlds in chunks is a well-known concept, basically since Minecraft. But there's a widespread misconception that, well, it can be used deterministically with algorithms where the surroundings of the chunk would need to affect the chunk itself. The logic of the argument goes that, well, if the chunk would need context, then you need to generate the chunks around it first, and they would need the chunks around them, and so on. So you need to generate all the chunks before you can generate one chunk, and of course that's a contradiction. But there's a way to generate chunks with context, and that's what I'll be talking about here. Yeah, there's a way, and it allows things like you could be blurring data, you could be relaxing distances between points, or you could be generating roads in terrain based on pathfinding, which can make them look more natural, and all seamlessly across chunk boundaries. I've developed a framework for this layer-based infinite procedural generation. I built it up, it's for C#, and it's called Layer Proc Gen, and I'll release it later this year as open source. But this talk is going to be focused on the underlying principles so that you hopefully understand like how it works, and if somebody wanted, they could implement it, make their own implementation elsewhere as well. Yeah, I want to show just a little teaser video giving an idea of what kind of thing this framework is about. It's a visualization I made last week. About myself. I'm Rune Skovbo Johanssen. I'm an independent game developer working mostly solo. I went solo since 2021 and I made a game called Eye of the Temple for VR, and it's using a little bit of procedural generation but at design time, not the kind of runtime procedural generation I'm talking about here. My new game that I'm working on has the working title The Big Forest, and you'll be seeing a bit of that in this talk. Before I went independent, I worked 12 years at Unity, working as a programmer focused on editor tooling and usability. And before that, I was at university. I wrote my master's thesis about semi-procedural animation for walking and running on uneven terrain. And it ended up getting cited in quite a few academic papers. So Layer Proc Gen, my framework was developed on and off over more than a decade, originally for a 2.5D platformer called The Cluster, sadly never released. But you can see that this is a platformer taking place in a vertical plane. My new game is a first or third person game taking place in an infinite horizontal plane, so the framework is not really tied to any specific kind of game. Here are the topics I'll go over. Also, I'll have to go through things a bit fast, but I have a link to the slides in the final slide. First topic, generating chunks with context. I'm going to show an example from the big forest where there's natural paths across chunk boundaries. And I first want to show a video where you can see what these paths look like. So you can see kind of natural looking paths going through the terrain. And when you get into parts of the landscape with steeper terrain, the paths begin to make switchbacks, like zigzag-like patterns, as an emergent effect because the pathfinding is using a cost function that penalizes steepness. And yeah, of course, this requires for the pathfinding to use information about the heights of the terrain in the surroundings around it. And now I'm going to show how this is done, basically by showing parts of the video from before again, but explaining what's actually going on. Sorry. We can switch the audio off for now if... yeah. So anyway. We have these different layers and location layer 0 at the bottom. No, it's still audio. I'm basically generating 3 different random points per chunk, so very simple beginning. In the next layer, for a given chunk, I take the points from the corresponding chunk in the layer below and also from the 8 neighboring chunks. And then do a point relaxation, meaning basically trying to make the distances between the points a bit more even. And I do that on all 9 chunks, but I then discard the results from the neighboring chunks and only use the ones from the center chunk and store that in the location layer 1. And because it's only using information from the layer below and not overriding that information, but storing the result in a new layer, the result is deterministic. In the next layer, location layer 2, I'm figuring out what the radiuses could be. If the radiuses had been larger, it would make sure that they don't overlap. So this does require all the positions, again, of the neighboring chunks, which is why we need yet another layer. Then in location layer 3, I'm creating connections, like deciding where should there be paths, which point should there be paths between. Excuse me. Within a chunk, I use the shortest distances that connect all 3 points in the chunk, and I also find for each of the 4 orthogonal neighboring chunks the shortest connection between a point in the current chunk and that neighbor. And of course, since, again, we're basing it on information about the neighboring points, we need a new layer so that we can get the context from the layer below, but only write into a new layer. Then we have the cultivation layer 0. Here it does the actual pathfinding between the points that we decided in the location layer 3 should be connected. So it uses that information from that layer. It also uses height information that is calculated in another layer called grid layer. So combining the height information and the points that should be connected, it can do pathfinding using this cost function that penalizes steepness in order to find a nice natural path through the terrain. Yeah, apart from that, there's more layers that I haven't talked about. For example, landscape layers that do path deformation based on the found paths and also generate the actual terrain objects. All right, that was an example, but how does the framework generally work? So this is based, like you need to be a programmer to use this for now, at least in my implementation. And you generate pairs of classes that represent a layer and the chunks for that layer. For example, location layer and location chunk, geo layer and geo chunk. in the base class of a layer, it stores a rolling grid for all the chunks of that layer. But when you implement a specific layer, you don't need to do that because it's handled in the base functionality. And to the right is some code, but I have to move quickly forward. The chunk lifetime is that when something depends on a chunk, it's generated, and if more things depend on it, it just stays there. When there's no longer anything that depends on the chunk, then it is destroyed or recycled in order to avoid allocations, but that chunk no longer exists. And the chunk generation, this is where you would have your custom procedural generation code. The framework doesn't actually do procedural generation. It's a framework for you to do procedural generation using whatever algorithms you want, as long as they are compatible with chunks. So in this generation code, a chunk can request data from a different layer. And the way this works is that it requests data from within certain world space bounds, and those bounds are going to be the bounds of the chunk itself, the user chunk, plus some padding, and it varies how much padding is appropriate. I'll get back to that. The layer that has received the request then figures out which of that layer's chunks overlap those bounds, collects the data from those chunks, and return it to the user chunk. And when I say user and provider, it's not like those are different types of chunks. It's just different roles in the context of a specific dependency. So typically a chunk could be a user compared to some data, but a provider of other data at the same time. So how do we ensure that the provider chunks exist when we need data from them? Yeah, they of course need to be generated when we need the data from them. And I found it's too much overhead to generate them just in time when a method call is requesting the data. It made it a bit unclear what the lifetime of the chunk should be. So instead, I settled on an approach where all chunks that need to be providers for another chunk are generated before that user chunk. This means that we need to know about the dependencies ahead of time before the user chunk is even generated. So in the framework, this is handled by specifying layer dependencies. We can redefine the dependencies between chunks as dependencies between layers. And in a layers constructor, you can specify once and for all which other layers that layer depends on, and with how much padding it depends on each other layer. This layer dependency and that amount of padding, it must be the maximal amount of padding of any of the actual requests that are being done in the code. And that's, it's possible I mean, this is something you need manually to ensure, but if you don't specify enough padding in the layer dependency and request data that's outside of what you actually told it you would need, then you will get, with my framework, runtime errors that will tell you, hey, you requested this data, it doesn't exist, you need to specify more padding. This is some example code for it. It looks like to specify dependencies on two other layers from the constructor of a layer. Another thing that you can do with this framework is to generate runtime procedural worlds that where you are generating at scale with intent. And what do I mean by that? So let me take a step back. There's not only two, but two types of procedural generation that I want to contrast, which is a functional approach versus a plan generation. With the functional approach, content is basically a local function you call a function for a given position and you get a result back. But the function doesn't really have any idea about the surroundings. And this approach is common in like open world procedural games like Minecraft and No Man's Sky. In contrast, the planning approach has generation that's top-down, so there's an intent behind the placement of items and how things are connected. And this is common in procedural games with finite spaces, such as roguelikes. There are some limitations of the functional approach. For example, a cave doesn't know if it's connected to the surface. If you have some vital resource on the top of a cliff, the approach can't know if it's actually reachable, if the player can fly. And games that use the functional approach work around this in a few ways, like by typically either giving the player very generous abilities to be able to always reach any point. For example, in Minecraft, you can just modify the terrain. Or by placing progression critical objectives at special trivially reachable spots. Essentially, it becomes a necessity to embrace a sandbox gameplay. But of course, not all games aspire to be of the sandbox type. We haven't really, at least as far as I'm aware, I haven't really seen any open world like infinite procedurally generated games using the planning approach yet. But this is something that this layer-based approach makes possible. Because with a layer-based approach, different layers can operate at different levels of abstraction, and this makes it feasible for some layers to generate vastly larger areas than other layers, just at a higher level of abstraction. I'm going to show an example from the other game I mentioned that I worked on way in the past, which has huge, carefully planned regions to explore. I'm going to show a little video to have an idea about the game. So there's an in-game map. You can see the immediate surroundings in fairly close detail to what the actual geometry is like. But if you zoom out, you see paths going through the region at a more abstract level. And when you zoom even more out, you just see the different regions in the world. This is a debug visualization of the maze layer in the game. You can see the different maze chunks here. So it creates like sort of maze-like path through the world that you can traverse. And sometimes there's locks and keys, something that would not work with a functional approach. If we zoom a bit out, we can see all the maze chunks that are currently generated at a time. Of course, when the player moves around, some will be destroyed, new will be created. And if we keep this zoom level but change to a visualization of a different layer called the region layer, it looks like this. You can see that this data is way bigger. So like one cell in this layer corresponds to an entire maze chunk in the other one. And this layer keeps track of like where are there shrines, which is a thing in this game, and where the artifacts you need to find, where's the central village, where's the gates to the other regions. In this screenshot, each different color is a different region. And so there's this large-scale structure to the world around the player that is very much intentional, like you need to find all the artifacts to be able to save the region and to unlock the gates to other regions and so on. And if we zoom out, this is a region layer, all the chunks that are loaded, and you can see that we can see now that there's actually many worlds around the world the player is in. If we then change to another layer called the world layer, those chunks are even larger. They control which worlds are there and how they are connected. And if we zoom even more out, we can see there's a lot of worlds, but the player will probably never get this far anyway. So my point with this is, it's not that necessarily that you could generate enough engaging content for the player to explore all this, but we do know that infinite games can be engaging if they are designed in the right way. And with this approach, you can have large-scale structure, just like many manually designed open-world games have. For example, the player might need to find some artifact in the east and go to the west and activate something with it. Or some regions are off limit for a long time, but later they get unlocked in the game. This is possible with infinite procedural games as well when using this layer-based approach. Another example here is that it can give a greater feeling of that the world feels like a real place with intent. In the game there are road signs that point towards nearby points of interest, like the shrines and gates and village. And this is possible because the region layer in each cell knows about the direction you would need to go to reach these points of interest. And the maze layer, a maze chunk, can query the information about the region layer cell it's in and get that information and then figure out at which points in its own maze-like paths are there junctions where you would need to place these road signs to point what direction you need to go to reach the points of interest. And again, this is something you don't often see in procedural games of this scope. But it does mean that the player can see references to things that are far outside of what is currently generated geometry. And you could also, for example, have an NPC that tells you about something that's way far outside of what's currently generated at a concrete level. All right. So now I'm going to go a bit more general again, talk about some basically software patterns for layers that I have found in my work of creating this framework and using it. So one thing is that I talked about different layers as separate things and said that when you query data from another layer, then which chunks the data is collected from is basically an implementation detail. But I also said, gave some examples where one layer clearly knew about the chunks of another layer. So the reason for this discrepancy is that there's a special case, which is internal layer levels, where a single layer has several levels of generation. And each of those levels is essentially like an independent layer, except the chunks are shared across the levels. There's no explicit data request interface between the levels, and each level is also assumed to depend on the neighbor chunks in the previous level. So this is just kind of a shortcut if you know that you want to get data from neighbor chunks of similar data, then you can choose to create a multiple internal levels of a layer instead of creating separate layers. Another thing is when you request data, there's need to be a bit careful with thinking about like what is it actually you want with the bounds you specify. So, for example, when we're talking about paths going through the terrain, if you need to do path deformation, like flattening the ground where the paths are, then the chunk that needs to do this work needs to get all paths that overlap that chunk so that the paths can seamlessly be deformed in exactly the same way on both sides of a chunk boundary. So it would need to request all paths that are overlapping its own chunk bounds. However, if you have a process that is decorating paths with, for example, adding railings or stones along the edges or something like that, then you would not want two different chunks that a path goes across to both do the decoration for the same pass, because then you have maybe set fighting or twice as much decoration as you need, or stuff like that. So in this case, the chunk user would need to ask for all paths that are kind of owned within its own bounds. And in order for this concept to make sense in a general way, you can, for each path, specify, well, which point is the ownership point of the path. And if, so the layer that's providing the data can check all the chunks that overlap the bounds and collect all the paths, but only return the paths where the ownership point, which could just be the center of the path, lies within the request bounds. Right. So those are kind of like different patterns. So if the layer that has the path need to provide both of those services, you'll probably want two different methods: one for requesting overlapping paths and one for requesting owned paths in bounds. Then to something else, I've glossed over. I've said like a chunk would request data from other layers with its own bounds plus some padding, but I didn't say how to determine how much padding to use. That's what this section is about. So basically, I've covered cases where you create some completely new kind of data based on a different type of data, but sometimes a process essentially feels like it modifies data because it has the same kind of data as input and output. So this could be initial pixels and you return blurred pixels, or initial points and you return relaxed points, initial heights and you return eroded heights. And we can think of this as modifying data, but of course we are not actually overriding any data since we're storing it in a new layer. And I need to hurry a bit. So we don't want chunk discontinuities, so we basically want to figure out what is the effect distance. And for example, for blurring, it would be the blur distance. So you need to request data with larger bounds so that you can blur it and only use the blurred data where there's no missing data. And if there's multiple iterations, you need to consider the effect distance of each iteration and add them together. A rule of thumb is that in any process you shouldn't have edge case code for handling the edges of the data. For example, in blurring, you don't need edge case code for handling the edges as you would normally have in a blurring operation, because this would create discontinuities at the chunk edges. Instead, we always request enough data that the more data than we output, so that all the data in the output has all the data it needs for its operation without needing any edge cases. You can also calculate this distance for other processes, like relaxing distances between points, as long as you have a maximum distance for how far away points can affect other points. And now that we thought about effect distance for modifying data, we can also think about it more generally. For example, for pathfinding, it's clear that the surrounding heights affect what pathfinding paths you will get, but how far away can they affect it? It's a little bit unclear. At least for me, it's not trivial to figure out how far away the terrain is going to affect the solution path. But instead, I just restrict the pathfinding algorithm to only consider points within a certain distance from the line segment between the beginning, the start and the goal point of the pathfinding. And so I just define my own effect distance, and then I know I only need to request the height data with enough padding to allow for that distance from the line segment. I think that is basically it. I don't know if there's time for questions.
Hi, really interesting. So I wonder if this framework can be used to, for example, generate exactly one road.
Exactly one road?
Yeah, one connected road across the entire infinite plane.
Yeah, you could do that by having in each chunk, for example, connecting the two opposing corners. Then I guess you would get one road.
Yeah, but if you want to have it twist all over the place and
yeah, at some point you need to specify a start and then for some pathfinding somewhere. But you could use really large chunks. I actually did this for a while, and it was very twisty passages. So I think that can work well enough.
Okay, thanks.